Imagine standing on the vast, blinding expanse of the Arctic tundra. The wind screams past you at 40 miles per hour, slicing through every layer of clothing. The temperature? A crushing $-45 degrees Fahrenheit, about $-43 degrees Celsius. The sun, if it rises at all, hangs low like a pale, distant moon, offering no warmth. This is the polar night, a season of crippling cold and interminable darkness, where the air itself feels lethal. Now, look around. There are no trees, no stone quarries, no natural shelters offering respite. Survival seems impossible. Death is a certainty. Yet, generation after generation, the Inuit and their ancestors did not just survive, they thrived. They built homes, warm enough for their children to sleep soundly and for their families to cook, socialize, and repair their vital gear. They did it using the very element that defines their perilous world, snow. This is the profound paradox. We instinctively view snow as cold, wet, and flimsy, the antithesis of a secure shelter. We build our wooden homes to withstand the weather, yet the traditional Arctic home is built from a material most of us would trust less than a pile of leaves. How could a structure built only from compacted frozen water provide better thermal protection than a thick, well-constructed wooden cabin, transforming a landscape of death into a haven of warmth? The popular imagination often paints a simplistic and, frankly, condescending picture of Arctic life, people huddled in simple, temporary snow piles, relying on sheer brute endurance. We see the igloo, the Inuit word, igloo, simply means house, as a novelty, a kind of primitive, temporary camp. This view is fundamentally wrong and profoundly disrespectful to the incredible intelligence of the ancestors. The truth is that the traditional igloo is not a symbol of primitive struggle. It is a masterpiece of sophisticated engineering, a silent testament to profound, millennia-spanning material science and architectural genius. It is not a random pile of snow, it is a meticulously calculated, self-supporting dome built from a specific, carefully selected composite material, operating on fundamental principles of thermodynamics and structural mechanics. What we are looking at is not just an emergency shelter, but a hyper-efficient, highly durable, portable, and custom-engineered structure whose thermal properties rival, and often surpass, those of shelters built with the best materials available to other pre-industrialized cultures. The real story of the igloo is one of meticulous observation, empirical testing, and the brilliant application of physics to conquer one of the most hostile environments on Earth. It reveals an ancestral intelligence focused not on brute force, but on thermal efficiency and elegant design. The igloo is an ephemeral structure. It melts, it collapses, and it leaves no permanent masonry. Therefore, the proof of this incredible structural intelligence lies not in preserved snow domes, but in the footprints of human activity and the specialized toolkit the builders left behind. Our story is anchored in the archaeological record of the Thule culture, the direct ancestors of the modern Inuit, whose expansion across the Arctic beginning around 1200 to 1300 AD was predicated on the mastery of this specific seasonal architecture. Archaeological sites across the Canadian Arctic, Greenland, and Alaska, from Tasiilaq to the Dorset Peninsula, show a clear duality in settlement patterns. Permanent, semi-subterranean winter houses, constructed from whalebone, sod, and stone, often featured long, cold trap entrances, clearly demonstrating an understanding of convection and insulation. These fixed settlements were used during the darkest, most stable part of the year. However, the Thule were also highly mobile, following migrating marine mammals like whales, seals, and caribou. It is during these long, arduous hunting trips and seasonal transitions that the snow igloo became the paramount dwelling. The evidence for its systematic use is found in the hundreds of temporary campsites, small scatters of artifacts, hearth remnants, and butchering sites, that lack the long-term investment of stone houses. The igloo was the perfect architectural expression of mobility, a structure built entirely from ubiquitous local material that could be erected and dismantled quickly, leaving virtually no trace. This mobility, enabled by the igloo, was the key to Thule's success across a vast territory. The most compelling physical evidence of the igloo tradition is the highly specialized tool developed for its construction, the snow knife, or Pana. Early versions of the Pana were crafted from massive sections of caribou antler or walrus ivory. These artifacts are diagnostic markers of the Thule and later Inuit cultures. Analysis of these implements reveals a complex manufacturing process. The material needed to be carefully selected for resilience in extreme cold. Brittle materials would shatter. The Pana itself is often long and slightly curved, designed not for simple cutting, but for creating the precise, tapered blocks necessary for the self-supporting spiral dome. Microwear analysis performed on Pana specimens recovered from sites like Marmot Creek in the Canadian Arctic shows heavy, repetitive scoring marks consistent with the deep, clean slicing of dense, wind-packed snow. This tool is the smoking gun. It proves that this was not accidental shelter building, but an industrialized, systematic construction process with highly specialized equipment. The Pana represents an investment of time, skill, and material that would only be justified by a technology, the igloo, that was absolutely central to survival and mobility. The engineering starts not when the first block is laid, but when the antler is carved into the perfect, durable blade. This archaeological reality establishes the foundation for a story of profound ancestral intelligence. The igloo is a culmination of environmental material science, structural engineering, and elegant thermodynamic design. To truly appreciate the genius of this structure, we must systematically break down its components. The foundation of the igloo's thermal efficiency is the careful selection of its primary building material. The builders did not use fresh, fluffy powder. They sought out snow that had undergone a process called sintering, or metamorphism. This typically occurs in older, wind-packed drifts where the repeated cycles of pressure, friction, and mild temperature fluctuations cause the crystalline lattice of the snow to rearrange. Sintering and density. This wind-packed, or board, snow has a much higher density than fresh snow, ranging from $300 /text, kg/m, $3 to $600 /text, kg/m, $3, which provides the shear strength and compressive durability necessary for bearing structural load. Crucially, even at this density, this snow is still approximately 90–95% trapped air. Thermal conductivity, $kappa. The insulating performance of a material is quantified by its thermal conductivity, $kappa. Air is an exceptionally poor conductor of heat, $kappa_text, air, \approximate 0.024 \text, w/m \text, k $. The wind-packed snow utilized by the Inuit has an extremely low effective conductivity, often $kappa_text, snow \approximate 0.05 \text, w/m \text, k $to $0.2 \text, w/m \text, k $. Compare this to a moderately dense hardwood like oak, where $kappa_text, oak \approximate 0.17 \text, w/m \text, k $, and the superior thermal property of the snow structure becomes evident. The dense, porous snow acts as a massive air trap, slowing the transfer of heat dramatically. The perfect block. The blocks were cut and tested empirically for sound. A high-pitched thunk indicated the correct density and lack of internal voids. This selection process was a masterclass in on-site quality control for a composite material. The blocks had to be strong enough to withstand cutting and handling but light enough to lift into position. The architectural brilliance is the use of the catenary arch in a three-dimensional, spiraling form. A catenary is the curve a free-hanging chain takes under its own weight. When inverted, it becomes the ideal arch because all forces are directed along the curve of the structure toward the ground, neutralizing internal tension. The self-supporting dome. Unlike a barrel vault or an arch, a dome distributes its compressive loads equally in all directions. By using a catenary profile, the Inuit ensured that the vast majority of the weight of the snow blocks was converted into compression. The force snow is excellent at resisting, and minimize tension or shear, which snow resists poorly. This is why the igloo requires no scaffolding, no internal supports, and no binding mortar. It is a pure, structurally optimized form. The continuous spiral construction. The efficiency of construction is breathtaking. The first course of blocks is cut slightly upward on a bevel, creating a ramp that the second course begins to follow. The blocks are trimmed into a wedge shape both horizontally, to follow the circle, and vertically, to follow the dome's curvature. This allows the builder to continuously lay the blocks in a single, upward spiraling ribbon. This spiral is not just faster, it ensures that the structural integrity is maintained continuously from base to apex, distributing stress evenly as the walls grow taller. The key block and final locking. The construction culminates with the key block, the final wedge-shaped piece inserted at the apex. This block, dropped or pushed into place, essentially locks the entire spiral in compression. The slight inward-leaning angle of the walls ensures that gravity itself drives the blocks tighter together. This structural finality is achieved in a matter of minutes, transforming a pile of blocks into a rigid, monolithic shell. A perfect structure is useless if its heat escapes. The internal environment of the igloo is managed through a calculated manipulation of air density and moisture control. The cold sink principle. The entrance tunnel to the igloo is always built lower than the floor level of the main living area. This is a brilliant application of the cold sink principle. Since cold air is significantly denser than warm air, any cold air that infiltrates the igloo drops immediately into the lowest section, the entrance tunnel, creating a natural thermal barrier that traps the warm, buoyant air within the dome. This effect can maintain a difference of $40°/circ/mathrm, c. $to $60°/circ/mathrm, c. $, between the exterior air and the warm sleeping platform. The ice glaze and thermal cycling. Once the internal temperature rises, powered by the oil lamp, Kudlik ***** and the occupant's metabolic heat, a human generates about 100 W of heat at rest, the innermost surface of the snow wall begins to melt slightly. This melted layer immediately refreezes into a thin, glassy ice glaze. This glaze performs two critical functions. 1. It creates an internal vapor barrier, preventing humid air from penetrating the porous insulation layer, which would compromise its performance. 2. It significantly hardens the structure, adding shear resistance to the inner surface. The external temperature, however, remains so cold, e.g., $40°/circ/mathrm, c. $, that this glaze cannot propagate through the thick, porous wall. The bulk of the wall remains low density, air-trapping snow, maintaining the superior insulation. Ventilation and moisture control. A small, critical ventilation hole is often created near the top of the dome. This is not just for oxygen, but for moisture exhaust. The breath of the occupants and the Kudlik lamp produce water vapor. If this vapor is allowed to build up, it will freeze on the inner walls, slowly making the insulation denser and less effective. The vent allows for a controlled, minimal exchange that exhausts the moisture-laden, stale air, keeping the integrity of the thermal barrier intact. This simple hole is the difference between a functional home and a slowly collapsing, freezing structure. The complete igloo, therefore, is not merely a stack of snow blocks. It is a closed, highly efficient thermal system, a perfect dome of trapped air, utilizing gravity, density, and phase transitions, melting and refreezing, to create a warm, dry environment against impossible cold. The igloo's genius extended far beyond simple survival. It fundamentally shaped the social and cultural architecture of the Thule and Inuit peoples. It provided a powerful foundation for a flourishing society in an otherwise prohibitive landscape. The construction of an igloo is a skill demanding intense spatial awareness, geometry, and a deep, intuitive knowledge of snow physics. This knowledge was not written down, it was passed down through rigorous apprenticeship. Young builders would learn by assisting masters, observing the precise cuts of the pana and the perfect slope of the spiral. The ability to build an igloo was a marker of competence, maturity, and readiness for adulthood, a skill as important as hunting or navigation. It created a highly knowledgeable society where expert engineering was a prerequisite for communal safety. Inside the dome, life changed dramatically. The relative warmth and the gentle, diffuse light filtered through the snow walls created an atmosphere of peace and psychological security against the terrifying blizzard outside. The circular shape promoted social cohesion. There were no corners, no distant seats. Families could dry their sealskin clothing, allowing them to maintain their vital hunting gear. They could cook a meal using the efficient Kudlik lamp, a luxury impossible in a truly cold environment. This secure, warm space was a sanctuary for storytelling, repair work, and rest. It provided the cognitive break necessary to recover from the high stress of Arctic hunting. The igloo was thus a critical component of mental resilience, transforming a landscape of constant threat into a place where the deep roots of culture could thrive. The quick, successful construction of a shelter immediately restored confidence, allowing the occupants to remain optimistic and focused on the next day's hunt. The ancient engineering wisdom of the igloo is not confined to the history books. Its principles resonate deeply with modern science, engineering, and the urgent demands of sustainability. The ingenuity of the ancestors offers critical lessons for our own time. Today, engineers and architects are grappling with the challenge of building truly zero-impact, thermally efficient structures. The igloo stands as the ultimate example of hyperlocal, fully renewable, temporary to permanent construction. It utilizes $100% local material, requires no imported resources, and leaves no permanent trace on the environment when it melts. This concept of build only what you need from the immediate surroundings is a core tenet of modern sustainable design and biomimicry. The lesson is clear: the most sophisticated designs often use the simplest, most abundant materials. The knowledge of igloo construction remains a cornerstone of modern Arctic survival training for military personnel, polar explorers, and scientific researchers. Expedition teams operating in the high Arctic regularly rely on igloo construction as the most reliable, warm, and secure shelter option when their primary tents fail or when resources are constrained. Modern scientific outposts, even with high-tech materials, continue to mimic the thermal principles perfected by the Inuit, especially the use of layered, low-conductivity walls and controlled cold-trapping entrances. Furthermore, the study of the thermal properties of snow is crucial to modern climate science. The igloo model provides a benchmark for understanding how ice, snow, and trapped air interact to regulate surface temperature, data vital for studying sea ice dynamics and permafrost stability. The ultimate lesson of the igloo is not merely one of survival, but of optimal design through deep environmental literacy. It teaches us that true resilience comes not from dominating nature with complex machinery, but from profoundly understanding its physics and working with its laws. The ancestors achieved an engineering feat that still defines the gold standard for thermal efficiency in the coldest environment on Earth. We began with a paradox: how could fragile frozen water protect life from the most lethal cold imaginable? The answer, revealed through archaeology, anthropology, and Thermodynamics, is that the igloo is not a primitive hut but a perfectly optimized structure built on genius principles. It is a spiraling dome of trapped air, a masterpiece of compression mechanics, and a brilliant application of the cold sink effect. The engineers of the Thule and Inuit cultures did not just survive, they created a mobile, sustainable civilization powered by a complete mastery of their environment's physics. They remind us that the greatest limits to human potential are not the hostility of nature, but the limits of our own observation. We look upon the white landscape and see only cold, they looked upon the snow and saw an inexhaustible, perfect building material. This profound achievement is a testament to the fact that human intelligence, fueled by necessity and respect for the natural world, is the ultimate force for innovation. But the Inuit were not alone in their cleverness against the cold. Next time on The Frostbitten Past, we travel to the Paleolithic heartland of Central Europe to uncover the astonishing architectural secrets of the mammoth bone houses of Dolny Vestinus *. How did our Ice Age ancestors use the remains of gigantic beasts to build massive, semi-permanent settlements that housed dozens of people? Subscribe to find out.